Here we go.
All right, so today's the last day, and we're going to be basically covering the major concepts that we talked about for this semester. It's basically going to be a big review for you guys, and then afterwards we're going to be talking about next semester stuff, future stuff for you guys as well as us, and then for the remainder of the class time, it will be dedicated to office hours. Project 3 is due midnight tonight. So it will be a good time for you guys to ask us questions if you need any help, and to collaborate together and basically use the time wisely. So yeah, so to just go right into it, the very first model that we learned is the linear regression model, and the model is based off the equation up there. So it's y equals to beta naught plus beta 1, x1 plus beta 2, x2, etc. All of these terms are additive. So linear regression is basically an additive model where we're just adding coefficients together. And in this case, each coefficient means something. Beta 1 would be the coefficient next to the first column, first predictive value. And you're multiplying the beta 1 coefficient to each value in x1 to get your transform value. And then you do the same thing for every other predictor variable that you throw inside the linear regression model. When you add everything up, you get your final y response. So that's linear regression. And in terms of interpretation, it's really important to understand that the coefficients are actually random. So if you throw in random subsets of the data, you will get different coefficients. And the question is, once you get a coefficient, is that coefficient different from 0? Because if that coefficient is 0, then according to this equation right here, that means that essentially that predictor variable has absolutely no relationship or influence on your response variable. So if it's actually 0, then we shouldn't care about it. It's only the variables that are not 0, the coefficients that are not 0, that we want to pay more attention to. So given that the coefficients are random, and also that the coefficients are distributed in according to the normal distribution with mean 0 and a certain variance, we can calculate the p-value of the beta value of each beta j and figure out whether that beta j is farther or a certain number of standard deviations far enough away from 0 to be considered significant. So p-value, again, the definition is given that the null hypothesis is true. Our null hypothesis in this case is beta j being equal to 0. What is the likelihood that we will see our current estimate of beta j being so far away from 0 or being not 0? So by dividing our current estimate of beta j by its variance, we can get a t-score, and then we can convert the t-score to p-value using a Python package, which is really easy. And so for us statisticians, we usually take a p-value of anything below 0.05 to be significant. It's completely arbitrary. You can take that number to be 0.1 or 0.01. As long as you're setting the cutoff point to be 0.5, you should be fairly good on in terms of interpretation and which variables are important or not. For logistic regression, very similar. Instead of the equation of y equals beta naught plus beta 1, et cetera, we have this transform figure. And the reason why we do this is so that we can convert the response variable not into a continuous scale, but bound between 0 and 1. So we did a little exercise early on this semester on realizing why that is the case. Basically, that equation up there will bind anything between 0 and 1. And what gets outputted is the probability of x, which is what we want in a binary classification type problem, the probability of something being 1 or 0. So that's logistic regression, is basically transformation of linear regression, and the interpretation is basically the same thing. You have p-values. Also, I forgot to mention before, if you have a positive coefficient, then any increase in that variable, the x corresponding to the beta coefficient, it will increase either the response value for linear regression or the probability / likelihood for logistic regression, and vice versa. All right, so the next type of model that we looked into are clustering models. So you guys learned about k-means and k-nearest neighbors, And these models are used to basically find distances, how close each data point is to each other on some kind of either visual map over here, or you can actually do it with any type of data. The whole concept is through distances, and if data points are close enough to each other, we will consider them as very similar, and we want to classify or do regression on similar points. And so this has natural extensions to natural language processing, which you guys learned before, and also recommendation systems. So think of Amazon recommendations, Spotify recommendations, Netflix recommendations. Your attributes, your tastes, your preferences are essentially these points over there, and you're just finding the other people that are similar to you. And that's how the recommendation algorithm will try to spot new movies or new products to recommend to you that you're most likely to enjoy, to buy, etc. So really, clustering has a really huge space in recommendation type problems. So it's not a model, but it's really important anyways. You guys were introduced to Kaggle Crossvalidation next. So once you have your training set data, how do you verify that your model is working internally before you try to bring in new predicted data from the outside world? So you do that through cross-validation. It's the best way to validate your results currently. And it's fairly simple. You divide the data set into a certain number of folds, or k-folds. In this case, we have 5. And you basically train on 4 of the 5 partitions, and then you test on the 5th partition. So that would be the first iteration. And then you train on another subset of 4 partitions, and you train on the second, on the last partition, and so on and so forth, until you get to test on every single partition exactly once. So every single data point will be tested exactly one time, and that's basically Kaggle cross-validation. You average the results, and then that will be the final score that you hope will achieve once you predict on the actual new test set. Any questions on that? Cool. And then we looked into decision trees. I like to think of decision trees as basically a series of if-else statements. So if we have this type of problem again, like age, has job, and we want to predict if the person owns a car or not, we basically look at each column and see where we can do our if-else splits. So for age, for example, naturally we can say that, okay, anything below the age of 19 we'll just predict to be 0, the person does not own a car. If the person is over the age of 18, then we're still not there yet. We still have 0s and 1s in our response column, so we need to divide up our data set even more. We can do that 2 ways, either sticking with the age column again and say, okay, well, if anyone is greater than the age of 40, we'll predict the person to not have a car, and anyone who's less than 40 but greater than the age of 18, we'll predict the person to have a car. Or you can use another column, say has job, and say that, okay, if the person is greater than the age of 19 but does not have a job, we will predict that person does not have a car. And if that person has a job, we'll predict that person has a car. So all of this can be graphed up and summarized quite succinctly in a decision tree visual like so. And so if you just follow the tree, basically from top down to the bottom where we have the individual nodes or leaves in this case, we can reach the decision that the model has chosen for us. But it turns out that a single decision tree is fairly bad in predicting on new test data because a single tree will essentially overfit to only the trained data. So in order to fix that, what people have come up with is basically building a bunch of trees. And these trees are made not on the same data, but on random partitions of or random subsets of the original data. And not just randomly through the rows, but also randomly through the columns. So you're basically subsetting, let's say, 80% of the rows and like 30% of the columns. You feed that into one decision tree. That decision tree will spit out its results. Then you do the same operation randomly again, and another random 80% rows and 30% columns to another decision tree, and then so on and so forth. You do this 500 times, 1,000 times. You get results over here for regression, like numeric results for regression, or in the classification case, you get the classifications for that particular problem. And then once you have all 500, 1,000 predictions, you can take the average of them for the regression case or the mode in the classification case to get your final prediction. So those are random forests, and and this basically foreshadows the ensembling slides that we had last week. And then the final model that you guys learned was neural net. So these are very, very hot and hyped up right now. But basically, you have a bunch of nodes created that have weights associated with them. And these nodes are organized in certain layers. This is the input layer, or the first layer of nodes will be the input layer. Then the second layer will be hidden, the first hidden layer, then the second hidden layer, and then finally the last layer will be your output layer after you, basically the last step of the neural net. So you feed the neural net the inputs of your data inputs on the left-hand side. The inputs will be transformed with the weights and other stuff inside each node, and then pass on to the next node. These values, again, these are all transformed numeric values. These values will be transformed again and pass on to the second layer nodes, and then all the way down to the last layer. And then this final prediction or final number will be compared to the response value, and then you can actually calculate the error from that. And based off that error, you can basically say, okay, is this good or bad? It's most likely bad initially, but if it's bad, then you can actually go back through this neural net from right to left and try to reduce that error through gradient descent. So that's back propagation. You go from left to right, from initial input to the output layer, and then from right to left by calculating the gradients or the slope downwards in the error value or whatnot, in order to try to reduce the end error. And then once you return to the left-hand side, you feed the inputs again with the new weights adjusted from the back propagation, and then you basically repeat this process over and over again. All right, and then finally we looked into SambaLing algorithms. These aren't models per se, but they utilize a bunch of models and try to combine the predictions from each one. So we looked at two different techniques on SambaLing. One is blending, one is stacking. So for blending, it's fairly straightforward. You have your train data here, your test data here. You want to split the train data into a local train set and a local test set. And then for every model that you want to consider to throw inside this blender, you train on the local train set, then you test on the local test, and also test on the actual test set data, such that you will have predictions, n predictions according to the number of models that you threw in the blender, by n columns and a certain number of rows for both the local test and the actual test data. And then for the second layer of your ensemble, most people use a logistic or linear regression, something simple like that. And then that model will only train on this portion of the test, this portion of the train set, which is comprised of your predictions, all the predictions from your original models. After that train is done, you test on the test data, and then you get your final ensembled prediction result. Stacking, slight variant, and you can think of this as analogous, as similar to cross-validation. You have your train data, you split it into certain folds. In this case, we have 2 folds. And what you want to do is you want to, for every model that you have, you train it on one partition of the, or sorry, not one partition, the partition that's not your test partition. So local train A here, and then you want to test it on local train B. You get the predictions here. And then you want to do it again for local train B, where you use this model to train on local train B, and then test on local train A, and then you get the predictions for local train A. And finally, you run this model on the entire data set over here, train on this entire data set, and make its predictions on the test set over here. And then do that process n times for however many models you have, and then you get these predictions for your training set and these predictions for your real test set. And then, just like in blending, you just use your second layer model, linear logistic regression, to train on these new training data and test on the new test data, and then you get your final ensemble result. Does it make sense? Any questions? So that was basically data science with Kaggle in, 20 minutes? That's basically all you need to know. And so for next steps, before I talk about us, for you guys, if you're interested in pursuing more machine learning topics in the future, depending on what major you are, if you're a stat major, you have Stat 154, which is the machine learning course under the stat department. And if you're a CS major, you can take CS 189 in the CS department. And both courses are sufficient enough for you to, if you want to learn machine learning, practical machine learning out in the industry, or want to do it for Kaggle, both courses are sufficient enough for you to get that started. So so yeah, that's my advice if you want to learn more machine learning. And then obviously you can continue working on Kaggle. Kaggle is entirely free and, in my opinion, better than the 154, 189 courses because they teach you a whole lot more stuff, given that you look in the right places, and it's a lot more fun as well. So yeah, and then for us, for next semester, we're happy to say that the decal will happen again. Philip will be teaching the course, and Joseph, I'm not sure if you'll be teaching, but you might be, right? Might.
Might be.
Yeah.
Are we planning to do like the exact same thing again?
What do you mean?
Like what we did this semester? It'd be a lot more competent at it.
Yeah, similar. Yeah.
Oh, also, wait, you said 189 and 154, right?
Yeah, 189, 154.
Also,
are there anything else?
Data 100.
Oh yeah, Data 100. Sorry. Yeah, Data 100 is a good class.
It's going to be less on machine learning, more on like a practical applications type stuff.
Right. So
and also a little bit of like big data theming stuff.
Yeah. So you have more hands-on approaches to not machine learning techniques towards data science or data analysis, but like I don't know. You're probably learning the hypothesis testing, t-testing, A/B testing, which are just really important, visualizations, that kind of stuff, and most likely a little bit of machine learning, but definitely not as rigorous as 154 or 189. So
this would be really good prep for the machine learning in that course.
Yeah.
And by the way, if anyone's interested in taking it, I know it hasn't been on the schedule yet, but we just got it on the schedule yesterday. So if you search for 100, it won't pop up, so make sure to search for C100 under computer science or statistics. I recommend searching for it under statistics because a lot more people are getting on the CS waitlist and that one might fill up, but the stats waitlist is not going to fill up and they're the exact same thing. So I'd search for statistics C100 if you're interested.
How are you processing the waitlist?
How many people are on the waitlist?
Yeah. Well, everyone's on the waitlist, right?
Yeah, no, we're not accepting people in the class yet.
So, you're actually going to go ahead and...
We're going to choose randomly from the people who meet the prereqs. You meet the prereqs, Robbie. Yeah?
One of the discussion sections or lab section is blocked. You can't waitlist on it.
Right. Which one?
It's the Friday from 2 to 3.
That's a lab, right?
It's a lab, yeah.
I have no idea why that is. Just waitlisted in their lab. Also, if you search the CS one of the 4 discussion sections doesn't pop up, but it does pop up the same section if you search the stats one. I don't understand. But right now, it doesn't matter which discussion. I mean, it won't matter what discussion or lab you choose anyway. You can go to any of them. You know, standard CS operating procedure. I don't know which one I'll be teaching yet.
the joys of missing.
Anyway.
All right. Yeah. So I hope you guys can go through the Cal Central mess for the S100 and your other classes. We have to go through it as well. But basically, yeah. Anyways, so that will be next semester. Time and location will be to be determined. And I'm not going to be teaching the course, but instead I'll be leading the Cal Kaggle team next semester. So for all the non-freshmen in the room, you probably heard of the Kaggle Kaggle team last semester in the spring, which I also led as well. And I'm going to be doing so again for next semester. And basically, if you are interested in joining the team and want to know more about it, I encourage you to come talk to me after class, or just wait until next semester during first gen for the Data Science Society at Berkeley. Also be there talking about the team, how it work, and what exactly we would be doing. So yeah, and let's see. So next is office hours. But before we move on to that, just want to say thank you all for taking the course. On behalf of all the instructors, I can say that we had a lot of fun doing this, and really enjoyed teaching you guys machine learning and all the interesting stuff that Kaggle brings to the table. And likewise for you guys, I hope you all found the course interesting, rewarding, and I hope to see some of you continue doing Kaggle in the future. So, thank you. All right. You want to say anything?
Yeah, thanks.